Okay, so here we got our gamma ray spectrometer, and I did another video on that. And here's some strips of Americium from an industrial smoke detector. And so let's start a spectrum with these, and we'll take a look and see how that works. See how that looks. Look at the gamma ray peaks, and should be interesting. Okay. Okay, again, these detectors are very sensitive, so I'm setting this source far away from my other sources so they don't interfere with it, and try to get it a little ways away because I don't want it to be continuously triggering. I don't want two photons to go through the detector at the same time very often. In fact, maybe I should get a little bit further apart. We'll just let this run for, I think I did my background for 8 days, so we'll run it for about 8 days probably. Remember, the longer you run it, the signal goes as the number of photons, and the noise goes as the square root of the number of photons. And so signal to noise goes as the square root of time, since the photon count is constant in time. And so the longer you run it, the better the signal to noise you get. Okay. So we'll see how that looks in a few days, about a week. Okay, so here's our Americium spectrum after 8 days. I'm going to run it a little bit longer before I compare it to the other ones, because I think I ran it for like, this is the background for 8 days and 11 hours or something. So here, see guys, you can see the green line, which is the background, which I ran for, like I said, 8 days and 11 hours or 13 hours or something. And the neat thing about this is I noticed even earlier in the spectrum it will kind of fit this background. It will scale it even if you haven't run the initial spectrum that you're trying to subtract the background from, which is the yellow part. It will fit it. I noticed even after a day it was kind of fitting this green curve to the yellow curve. And so this is the Americium spectrum, and it looks like it says Americium 59 keV chain of Americium, and there's some, I don't know, some other spectra in the libraries. Okay, so that's linear scale. And I noticed here, if you go into let's see, is it dot dot dot? No, it's not dot dot dot. It was the gear setting, I think. Yeah, if we go down here, and so somehow I got into this other mode where you can just have it subtract off the background, and then you click save at the bottom. And so that's what our background looks like. This is log scale, of course. If I put it on linear, that other stuff is not so noisy. And you can see what the spectrum would look like without the background, or with the background subtracted. Okay, very cool, huh? And so this spectrum actually looks very different than the uranium spectrum that I was looking at. Even though I don't see the individual peaks, the uranium spectrum had some more signal at the higher frequencies, a very broadband signal, where this one looks like a couple extremely narrow peaks, one there and one here. So one about was that 27 kilo electron volts, and another one, see if I can get on the peak, which it doesn't seem to want to go. It's a little bit less than 75. For some reason I can't seem to grab the other cursor. Okay, there we go. Okay, so about 66 on this spectrometer. So the main peak looks like it's about 66. Okay, and so we can go back into the gear. I kind of like it on the other setting. And we'll just draw the background over, and of course this is linear scale. If I double click on the screen, it will go back into log scale. And there is our two peaks and our background, and if you pinch your fingers, you can scale the, pinch your fingers on the screen, you can scale the spectrum over the full range. Okay. Anyway, very cool. So this is our second baseline spectrum, and I'll continue doing these spectrum until I get all the all the knowns that I have, the sources that I have characterized, and then I'll be able to use this hopefully to look at unknowns and try to figure out what they are. Should be interesting. Okay. Okay, so I exported the data from our gamma ray spectrometer, and I plotted it against the uranium data that we took before. Okay, and this is the full range right there, and the blue one is the Americium, the new one, and the red one is the uranium. And I kind of zoomed in over the range of interest because most of the stuff at the high energy is flatlined. And this is a log scale. I plotted this as log, or I guess it'd be semi-log. It's log in the vertical direction and frequency, or energy, however you want to think about that, keV, in the horizontal direction. And the spectrum looked very different, right? The Americium, so if you had two unknowns, you'd be able to tell the difference between the two, because the Americium has a spectral peak that's much lower, and it's very clean up here. It has no radiation up here. Uranium has a higher energy peak and another peak up here. Okay, so our spectrum looked very different for the two different cases. That's very interesting, huh? And I'm going to be doing some more cases so we can compare it. But this is Americium and uranium. Okay. Okay, again, here's our chart of nuclides, and I'm kind of zoomed out here to show you where we are. I'm going to zoom in, and okay, let's see. Let's zoom in to here. And so uranium, Americium comes from uranium. So they have uranium in a nuclear reactor, and it's uranium-238, and it absorbs some neutrons, 239, and I guess it will decay, so it could absorb a few neutrons like so, and then decay. Let's see, does it say beta? This would be beta, this would be beta, and that would be it could be alpha or beta, so it decays beta again. And so then you could get to Americium-241. Okay, and so that is how you can get Americium from uranium. So uranium's here and it absorbs some neutrons. It's 238, which is the majority uranium. Absorbs one neutron, it becomes 239. Another neutron becomes 240. Another neutron becomes 241. I mean, it could take different paths, you know, it could maybe absorb a couple neutrons, beta decay, absorb another neutron, beta decay, but eventually it will get to Americium-241. And so here's our element that we're looking at right now. So this one came from a nuclear reactor. And that's how you get Americium, because it's not formed in nature naturally. Okay, very cool, huh? Anyway, so understanding the chart of nuclides and the radiation spectrum is very important if you want to do some experiments in radiation. Remember, radiation is your friend. It's the only possible thing that can replace fossil fuels. You know, maybe we build some nuclear powered batteries or something. Be very cool, huh? Anyway, but you have to understand the basics, the chart of nuclides, we'll probably be using this radiation gamma ray spectrometer to do some other interesting experiments. We'll do some transmutation with it. I'm going to do some more unknowns, so if you're interested in seeing that, I'll be doing, let's see, I've actually already made videos for, let's see, uranium, Americium, thorium, and radium, and I'm working on cobalt right now, so we'll have much more spectrum soon to come. Very cool, huh?